Hi, I'm Katie Steckles.
And I'm Peter Ollett. And Katie, what's today's mathematical object?
Today's object is an Arbelos, which is a shape that has a name and is a thing, but is quite difficult to describe, which is why we've brought along a special guest who is going to tell us all about it. Welcome, Kat.
Hello, my name's Catriona. I am a maths teacher coming to you today from school, but also in my spare time very interested in 2D shapes, which sounds terrible as a hobby, doesn't it? What I like to do with my 2D shapes, I draw pretty pictures of geometrical figures, generally in the form of a puzzle, and post them on Twitter. And one of my favourite 2D shapes is an Arbelos, so which I hope I'm pronouncing correctly. I don't actually know, but shall I describe the shape for you as best I can?
Have a go. Yeah.
So I think of the shape as being built out of 3 semicircles. So you take a semicircle and you put it on a flat horizontal kind of table. You've stood your semicircle up, and next to it you put a second semicircle. So they're just touching at one of their corners. Do semicircles have corners?
That's a matter for debate, yeah.
Having introduced myself as a shape expert, I don't know. Anyway, one of its corners, we all know what we mean. So they're just sitting touching each other. And then over the top of both of them, you draw a third semicircle. So it's going to just touch the 2 outer kind of corners of your 2 semicircles, sitting on the same base, so that all 3 of them share the same diameter. Does that make some sense?
It's fascinating how you see these things, because when you said 3 semicircles, I'm like, yep, one big semicircle divided up with 2. You've done it completely. You've done the 2 and then wrapped a big one around it.
Yeah, that's true. You could pack little ones in. Yeah.
Yeah, well, the picture I've looked at online has a big semicircle, and then there's an R distance across it, and so it's that R makes another little semicircle, and then 1 minus R makes the other little semicircle. So it's obviously the big one is a 1 unit diameter, and then that's separated into 2 parts, R and 1 minus R, which are the diameters of the 2 smaller ones. So I was totally seeing a big one with 2 little ones inside.
That's true. So we could also think of it as 2 smaller ones, kind of sharing a tent.
Yes.
Yeah, that's good. I've described it to people as a semicircle with semicircles cut out of the bottom, but then I realised you need to be slightly more careful than that, because the 2 that are at the bottom need to make up the whole width of the big one, I guess. So they touch in the middle, or not necessarily in the middle, they could be 2 different sizes, but they both touch the outside edges, and then they meet somewhere along that kind of like halfway line.
And what of this is the Arbelos?
Yeah, I was just thinking that, because Katie's description is quite a good one for that, having 2 semicircles cut out, because it is the leftover part that is the shape, that is the Arbelos. So it's this weird curvy shape, isn't it? Because it's got 3 sides, but all 3 of its sides are semicircles, like the circumference part of the semicircle. And it's got 3 corners, if we're going to allow corners. Yeah, like that. I think they're corners. So 3 sides, 3 corners. So it's kind of like a triangle, but with semicircles rather than straight lines.
Yeah.
In fact, I think there's some kind of hyperbolic geometry in which this is a triangle, but I don't know enough about that.
Yeah, it feels like a triangle, but with all of the corners touching the hyperbolic half-plane edge or something. And you get these nice semicircle curves, because semicircles are straight lines there, I guess, so... Yeah, that's cool.
That's good hyperbolic geometry. It's also definitely an umbrella over these 2 little semicircles.
Yeah.
It's like a slightly broken umbrella with the middle not quite in the middle. Or something.
Well, that's one of the reasons that I really like this shape, because it doesn't have to be symmetrical. I mean, it can be. Your 2 small semicircles can be the same size, but it doesn't have to be, and it sort of feels like it has a nice level of asymmetry. Because the semicircles themselves, they're very symmetrical shapes, but when you put the 3 of them together, you've got this kind of asymmetrical shape, and I think they're quite pretty. That's one of the reasons why it's my favourite shape. It's very easy to construct and draw, but they're kind of pretty, and it's weirdly asymmetrical.
I'm just really enjoying the idea that the 3 points at the bottom are corners, because I hadn't even thought of them as corners, but that's kind of what they are, because it's a shape which otherwise has only got kind of curves not necessarily straight edges, but curved edges. It reminded me of a thing that I saw a little while ago where there was a primary school maths question that was a picture of a semicircle, and the question was, does the shape contain any right angles? And the answer that the teacher was looking for was, no, of course it doesn't. It doesn't contain any right angles. And I was just about to teach a university lecture where I was defining the angle between two curves as being the angle between the tangents at the points where they cross, which obviously means it does have two right angles. So I guess the question is, how good are you at maths? In which case it does have two right angles, or it doesn't. But yeah, the angle between a curve and a straight line, or the angle between two curves, is slightly more complicated, I guess. Yeah.
And if you extended that to the Arbelos, all of its corners are 0 degrees by that definition.
Yeah. Yeah.
So 3 corners, but no degrees. Okay.
Yeah. It's a weird triangle in which the angles add up to 0.
Yeah. So the name of it apparently comes from a shoemaker's knife. And I did a quick Google search for these kind of knives, and the knives themselves, they have a blade that looks like a sort of symmetrical Arbelos, with sort of 2 wings almost and a big curved edge round, and then the middle corner, I suppose, should we call it, that's where you attach the handle.
Right.
And so it's apparently the Greek name for this kind of knife. Although when I went to my Greek friend to ask her how to pronounce it, and she didn't know, and she had not heard of this knife, but apparently that's where the name comes from.
Yeah, I always imagine leatherworking tools have to be pretty seriously terrifying objects, because leather's quite a tough substance to cut through, so if it's for shoemaking, yeah.
Yeah. Anyway, so one of the reasons that I like the shape is because it looks very pretty, but mainly because it has really cool properties. First thing that I kind of ever found out about the shape was its area. So to find the area, like you'd think to find the area, you need to know the area of the big semicircle and then the area of the 2 smaller ones that you've cut away from it. So 3 measurements really would be enough, like if you measure all 3 diameters. Or I guess you could measure the 2 smaller diameters and use that to work out the big one, or vice versa, but at least 2. But it turns out you only need 1 measurement to find the area of the Arbelos, which is, if you draw so we've laid our Arbelos out so that all 3 diameters are horizontal, haven't we? So we're going to draw a vertical line out of the middle corner, straight up until it hits the top of the large semicircle, which won't necessarily be in the middle, like it won't necessarily be at the highest point, but just straight up, kind of like the tent pole in this big tent. And it's just the length of that tent pole. The length of that vertical line is enough to find the area. And I think this is super weird because you can imagine loads of very different looking Arbeloses. Is that the plural? Arbeloi? I don't know.
Arbelopods. Yeah.
But anyway, lots of different ones. So the symmetrical one where this vertical line is the entire, right up to the highest point of the semicircle. Or one where, say, one of the small semicircles is 1 metre and the other one's like 1 centimetre. And so you've got a 101 centimetre diameter semicircle drawn over the top. But actually, like the vertical height that you get there is not going to be very big because you're so close to the edge. And so any 2 shapes any 2 Arbeloses where that vertical height is the same, they're going to have the same area overall.
I was just my initial instinct was to go, what are the edge cases here? So the one where it's in the middle, I guess you get the radius of the big circle, which if you know that the meeting point is in the middle, that should be enough to work it out, because you just need, that tells you what the radius of the smaller circles was. But then if it's 0, which is the other degenerate case, I guess you've got one semicircle that is just the other semicircle. Like there's one that doesn't exist and one that takes up the whole thing. So in that case, the area is 0, so that works as well. Yeah.
But it's one of those things where you think these 3 things are independent, but like one of them is the whole, and one of them is a fraction of that whole, and the other one is the other bit of that. So they are sort of all related, aren't they? So by making this height, you're kind of defining I don't know how that encodes all 3 bits of information that you need. So but
I can sort of imagine a GeoGebra animation where the point where the two bottom semicircles meet moves left and right, but at the same time the size of the bigger one grows and shrinks to keep the length of the line the same.
Yeah.
Oh,
They
okay.
sort
I
of
thought
slide
kind
through
of-
each other. Yeah.
Do you know what I mean? Because if your point moves so that it's nearer the middle, that line will get longer. But if you do that and then make the bigger one smaller while you're doing it, then the area will stay the same.
I was thinking you were imagining a diagram where, as you move the point between the two semicircles, the line shrinks and grows to try and get some.
Well, yeah.
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 Because you're
Any
sort of
these,
defining
yeah.
a triangle, aren't you? You've got the height of the thing and the two sides of the semicircle, the two corners, as we were calling it.
Yeah.
Yeah, and I guess that would be a right angle at the top because you're joining the two ends of a diameter to a point on the side. I remember circle theorems.
Yeah.
Um,
Yeah.
That'll give you a right angle at the top.
You can do really... So you can prove this entirely using Pythagoras' theorem. And on Wikipedia, there is a very nice... On the page for the Arbelos, there's a really nice proof without words where they use Pythagoras twice with semicircles rather than with squares on each of the sides of the right angle triangles. And they do it for the whole thing, like you just described, and for kind of one half, I suppose. So with the vertical line as a short side, and then for the other part, and put all of those together. It's very clever, but I don't think I could describe that in an audio way. So possibly people should
that's
go.
what
and
show
look it
notes
up.
are for.
Yeah.
Yeah, we can put a link in the notes for people to go and find it. Yeah.
Yeah, no, it's. I mean, these kind of invariant areas, I think that's really clever. This was the first time I ever came across an Arbelos because I was just sort of drawing, like playing around with semicircles, and I made this arrangement and I realised that is the only measurement you need. I thought, this is so cool. I'm going to draw this and put it on Twitter as a puzzle, can you find the area of the shape? And somebody replied saying, oh yeah, this is an Arbelos. And so that's how I found out about them, because I thought I discovered this amazing area theorem for myself, but no, of course not. Archimedes got there first. Or
So
it was attributed
the
to
idea
him.
that I might be able to name this after myself. No, sadly taken.
Yeah, no, it's super neat. In fact, there's more, because not only is that measurement enough, but the way that you then find the area. So it turns out that the area is the same as a circle that has the diameter of our tent pole. So the diameter of that vertical line, if you drew a circle in there, that circle has exactly the same area as the Arbelos. So that's how you find the area.
Right. I'm mentally adding this to my GeoGebra that I'm making in my mind.
Yeah, I mean, and that circle has loads of cool properties of its own, which we will no doubt come on to. But like, I guess for the symmetrical case, we could kind of work this out, because so in the symmetrical case, we've got two that are two little semicircles, each with half the diameter of the big one. And so using kind of area scale factors, we could say that, well, if their diameter is half of the big semicircle's diameter, its area is going to be a quarter, half squared, of the big semicircle's area. So we've got two semicircles, each with a quarter of the total area, which means the remaining area in the Arbelos is a half of the total area.
Of a semicircle.
Of the semicircle.
Yeah. And then your extra circle has diameter, the radius of the semicircle, because it's the vertical height in the middle. So that's going to have half the area. No, it's going to have a quarter of the area.
Yes.
Of the whole circle.
Yep, which is half the area.
Which is
of
the same as
semicircle.
half the area in the semicircle, yeah.
Yeah, that possibly too much arithmetic for people to follow along, but that, yeah, no, that, so we can prove it in that case. Anyway, it turns out that is also true, and if you want to prove that this stays the same, then using Pythagoras' theorem is probably the best way to go about it.
That's really cool.
It is. Should we talk about tangents?
Yeah, more cool stuff. That's exciting. Yes.
Okay, so we want to draw a tangent within the Arbelos that's going to be tangent to both of the two small semicircles. So, like, we're getting a plank and balancing it on top of these two small semicircles. So it's going to kind of run across the Arbelos. So it's going to touch each of the small semicircles once, because it's resting on both of them. this plank, the distance between those 2 points of tangency is the same as the vertical height that we drew in earlier.
Amazing. Yeah. I mean, I can imagine it. I mean, I don't even need to see it proved. I'm quite happy that is just a wonderful fact. But if you want to prove it, that's also fine.
Oh no, I'm not going to prove it, but I will go further.
It's a wonderful fact.
Not only are they the same length, they're actually, so that tangent between those 2 points, so tangent between where it touches both of them and the vertical line, are in fact two diagonals of the same rectangle. That's why they're the same length. So they form, so those 4 points, the kind of middle corner, the vertical point, the point vertically above it, so the top of our tent pole, and the 2 tangent points on the small semicircles, they form a rectangle. And in fact, that rectangle is inscribed inside the circle that we drew earlier.
Nice.
The one with diameter of the tent pole.
The one with,
yeah,
exactly.
So if you draw that circle, it will cross the 2 little semicircles at the points where a tangent resting on top of them would hit them.
Yeah. Yeah.
This is so cool. I mean, I'm especially enjoying the idea that people watching along might just be constructing this with a ruler and compass as we're talking. They might just be drawing this diagram.
I mean, I do think that's probably the best way to find out about shapes, is to try and draw them, because you often discover quite a lot, don't you? When you try and draw something, you discover a lot about what needs to be the same and what doesn't. That's kind of my general approach when I'm trying to solve geometry problems that I don't have a clue about. And how would I draw this? Because especially when you're trying to draw things with a ruler and compass, that really makes you focus on what needs to be the same length as something else, and all those little things.
Can I ask you about geometry? I'm never quite sure where geometry is in our school curriculum in this country. I see a lot of mathematicians in America being very geometry heavy, and I do remember being in sort of earlier years at school doing some geometry stuff, but I think it sort of petered out as it went along, and certainly at university
it does, doesn't it?
A bit strange.
It kind of dies. Yeah. So you get up to, you're right, I think GCSE you get up to circle theorems and kind of proving them and doing a fair bit of this stuff.
Yeah.
And then that whole area sort of dies off, and once you get into A level, it's focusing on trigonometry and kind of making everything much more algebraic.
Yes, and that's what happens at university. We do trigonometry, but more from an algebraic point of view, so it's harder to, I think.
Yeah. I'm trying to work out what happens in between, because I definitely know people who do geometry at research level, and it's like, cohomology and like, Poincare conjecture, it's like really weird abstract stuff, but it doesn't feel connected somehow to the sort of shapes and angles and things. But...
Yeah, I taught somewhere once where somebody suggested a final year module on geometry, and it was a bit like, like 100 years ago, that would have been entry level stuff, but suddenly now we don't teach it, so it's not. It's very strange.
I do have to admit that I think the first course that I dropped at university because I didn't understand what was going on was geometry.
Right.
It was just symbols and pictures, and not helped by a lecturer whose handwriting made it really hard to follow. I genuinely didn't, but I didn't understand enough to be able to work out what was going on. Yeah. So that was the first course that I ever stopped going to.
So what happened between then and now? At some point you've started...
Well, yeah. That kind of geometry, I think, though, was quite different to what I do now. It was sort of like what you're describing. It didn't really bear much relation to shapes, or at least not in my head, which probably shows how little I understood what he was going on about.
I feel like there's often like nice analogies and nice connections you can make, and the only thing I sort of remember vaguely was the idea of things like Galois theory, and the idea that it tells you which polygons are constructible with ruler and compass. And that was the only time that kind of constructions and angles and lines were even mentioned at university. But yeah, it's probably something that could be kind of more directly drawn out and connected to. But I guess the kind of geometry you're doing at school is the sort of useful, practical engineering stuff for like, how big does my rectangle need to be? Kind of thing, and complementary angles and things. Yeah.
In a way, I like the fact that there is this gap, because I think that's the only reason that an audience for my Twitter puzzles exists. It's fairly low entry, you need to know Pythagoras' theorem and probably a few circle theorems. I've learnt a lot of circle theorems from Twitter, but you know, you only need maybe a couple. And with that, you can kind of solve these things that don't seem obvious. And maybe if we did more of it at school, no one would be interested, because it would be the equivalent of just seeing bits of the A-level curriculum posted for fun, which, you know, I guess might be fun, but I don't think it would be as fun for as many people. And equally, university level maths probably doesn't look as fun for as many people because it doesn't seem as accessible. So it's kind of nice that this gap exists, and it's also nice that it's a gap that involves pretty shapes, because I do like colouring things in.
Yes.
Yeah, well, I think it's also quite a good type of puzzle, because you come at it with the set of tools that you're sort of vaguely aware that you have, like Pythagoras' theorem, but you often end up looking at a thing and you just know that at some point you're going to go, oh, that's the same as that, or like something is just going to click that makes the whole thing fall into place. But it's never immediately apparent what that's going to be. And it takes a bit of fun and sort of constructing a couple of things, and maybe if I drop a vertical from here or whatever, and that kind of unlocks it almost in a quite tantalising way.
Yeah, and there's a sort of joy in being able to discover these things that you hadn't realised before, which I think you get quite quickly. Like Katie, I feel like you had it when I said the tangent points are the same distance apart as the vertical line.
So good.
Yeah, there's all these things that don't seem immediately obvious, and then you think, oh wow.
So what happens when you're setting one of these? You're sort of doodling. Is it that you notice something, or is it that you're constructing something and then removing a bit of the construction to make it less obvious? Or how do you sort of come about it? You seem to have a...
That's a good question.
Thank you.
Yeah. I don't know, but sometimes a bit of both. Yeah. So I spend a lot of my time drawing little pictures, you know. I'll sit watching TV with a book in front of me and just kind of draw little shapes, and often starting from something that I know works, so a construction that I've got in mind. So I'm a big fan of puzzles where the solution, or a possible solution, is that you can join a load of points up in a circle, but you didn't realise the circle was there. So you've got, for example, lots of lines that are all the same length, and so obviously they must lie on a circle. Well, I say obviously, but it's not obvious when you look at them. So I quite like that kind of thing. So I'll start by trying to construct something along those lines, draw a load of lines the same length, and then think, well, how could I show people these are the same length without saying, oh, these lines are all the same length, and work from there. That's probably where I start most of the time. But sometimes I just draw a load of shapes next to each other. None of it's very thought out. I had this discussion with one of my colleagues the other day, because I'd posted a load of pictures on Twitter of like coming up with a puzzle. Somebody challenged me to, I bet you could think of a puzzle based on this, and I thought, I will, but I'll take pictures along the way. And I did, and it was a right mess, and the puzzle ended up miles away from where it started. And one of my colleagues saw it, and she said, I was really surprised, because like, I know you do this, and I just always imagined you just drew the shapes the right way the first time. But obviously you don't do that. Yeah. But in my head you always did do that. And yeah, lots of it is very, I guess, just trying things until they work. Isn't that a lot of maths?
That's much more playful and creative. That's not, if you just sort of had a firm idea and just wrote a thing down, that's much more... Yeah. That seems less interesting.
I mean, right? Very, very occasionally, just as I'm falling asleep, an idea will hit, oh, wait a minute, I could draw it like this. And if I'm lucky, I wake up the next day, I'm like, I remember that I thought of, and I draw it and it works first time. But that's happened to me maybe twice. Right. And the other 400 times is all just trying to build something out of somewhere. But yeah, it's playful. It's supposed to be fun, isn't it?
So one thing I've always wondered is, because I guess one question would be, what proportion of the time does the answer work out to be just some really nice, neat fraction or nice, neat whole number? And what proportion of the time is it just some kind of random value? Because you sort of want to get an answer and be like, it's that's good, and you can maybe put it back in somewhere and see where it fits. But sometimes you see these puzzles and you've got all of these things that are the square root of something and loads of other things, and then you put it all together and it just cancels out and the answer's a quarter or something incredible, and that's like a really nice, satisfying resolution. But I saw a puzzle the other day where someone was like, I've solved it, the answer is 31 point and some massive decimal, and I was like, great.
Because sometimes I
Nice.
draw things and I think, because sometimes it comes from, oh, I wonder what the biggest square I can fit in a regular hexagon is, or something like that. And sometimes I have these ideas, oh, I wonder, you know, if I arrange things like this, you can see there must be an answer, because there's kind of quite clearly only one way that this could possibly fit together. And then you start working it out and it's like, oh, the square root of 3 plus the square root of 2, all, you know, and yeah, I don't know, I'm not so interested in that, because I feel like when, like you say, it all cancels out and it's magically a quarter, and then you think, why on earth is that? And then you start to look for it, and is there a kind of, and more often than not, there's a really kind of simple, I'm doing scare quotes around simple, which no one on the podcast will be able to see, but simple as in can be done in 2 lines if you happen to spot it that way, but nobody in their right minds would see that as their first solution. But often it is there, and you'd only go looking for it once you know the answer's a quarter or something equivalently simple.
Yeah.
There's a joke, which is that a lecturer is giving a lecture and comes to a point and said, and the proof of this is simple, and then looks a bit puzzled and walks out the room and comes back 20 minutes later and says, yes, it's simple, and carries on. It's a bit like that. Once you know what you're doing, it's simple.
Yeah.
Yeah. Well, I mean, I guess you can decide what the question is as well. Like, you know, you're not going to say what's the length of this line if what's the area of this square is a much more interesting answer or whatever.
Yeah. Oh, definitely. I think that's... I have all these kind of self-imposed rules. I mean, there are no rules about what constitutes a Twitter puzzle, but I feel like I've sort of built my own niche of these are the kind of puzzles that I post. So I have my self-imposed rules, and one of them is it has to be a nice answer. So to be honest, I rarely go for anything that's not a whole number or like a very simple fraction, or a multiple of pi. Pi's are fine. Yeah, but you know, like you can make quite nice puzzles that have slightly more horrible answers, and that's fine.
Yeah. I'm just imagining now like an advent calendar with a puzzle on each door, and the answer to each puzzle is a number between 1 and 24.
Yeah.
And you can't decide which door to open until you've solved all of them, because you can't, like, which one of these has got the answer 1? I can't even open the first day.
I made my dad a birthday card recently for his 60th birthday that had a puzzle on the front where the answer was, it wasn't actually 60, I think it was 60 pi, because it involved circles.
Right.
It was the 0. Yeah. But anyway, I was very pleased with this. And my husband said, oh yeah, you can, why don't you make a whole range of cards where each one's got an answer that's each of these? And so I thought, oh yeah, that sounds really fun. I could do this for everybody's birthday. And then I started doing it. It's really hard. So, you know, there's maybe 2 ages that I can do now.
Well, I was going to say, I know people that have a, you know, maths toy shop that would quite happily stock a line of geometry puzzle birthday cards.
If I ever make anything vaguely comprehensive, I'll let you know.
So we've been talking about these brilliant puzzles that you post on Twitter. How can people find those?
So I'm on Twitter at cshearer41. That's CSHEARER 41. You can tell I didn't mean to become famous, can't you? I feel like I've got quite a following and I have a terrible Twitter handle. But yes, I post lots of puzzles on there, especially in school holidays. So that's a nice treat for all you other teachers.
Fantastic. And we are both also on Twitter. I am at Stex.
And I'm at Peter Rowlett, and the podcast itself is at Maths Objects.
And both Peter and I blog at aperiodical.com, which is where you can find more episodes of the podcast.
And if you'd like to talk to us, if you've got any interesting geometry you'd like to send our way, you can email us at objects@aperiodical.com.
The music is Funk Game Loop by Kevin MacLeod, licensed under Creative Commons.